Hello and welcome. This is the Taming Wild AI channel, where we bring AI technologies out of the wild using the best practices of software engineering. In this episode, we're going to take a segue from efficient neural architecture search. That repository exposed the fact that useful and interesting AI technologies were built using TensorFlow 1, but they don't work with the latest version of TensorFlow. The first thing to note is that writing code in TensorFlow 1 was counterintuitive for most people, not just data scientists. This is because Python is an interpreted language that many people use either in a Jupyter notebook or in a console like this. There are certain operations that Python performs immediately like this. Here, we're performing an addition immediately with values known right now. This is known as immediate or eager execution. And if we do something silly like this, we get an error immediately. There are other operations that Python performs later, like this. Here we've defined the addition operation for execution later. We can't get a result until we've specified the values for x and y like so. Now, suppose we were not allowed to get an immediate result by typing 1 plus 2. Then we would have to manually write out the plus function and then call it with 1 and 2. Now, suppose we were unable to get an immediate result by typing 1 plus 2, and we were unable to manually write out the plus function. Perhaps some people at Google would give us a function like this. Then we would call the function to get a quote-unquote computation graph. Then we would execute the graph on actual values to get the result. TensorFlow 1 was a lot like this. You had to call its functions to get a computation graph, and then execute the computation graph on actual data. You may be asking yourself why. In this analogy, the graph is nothing but a single Python function named addition graph. But TensorFlow could be used to compose an arbitrarily large and complex computation. Once it knew all the computations that were planned, TensorFlow could parallelize, schedule, and otherwise optimize them for fast execution on specialized hardware. There was really nothing better at the time. This approach is known by a few different names: delayed execution, graph mode execution, or even lazy execution. The downside was that it was easy to create a computation graph that would fail to execute on a given input. And when it did fail, it was hard to trace the failure back to the TensorFlow calls that were at fault. TensorFlow 2 restores the immediate feedback of eager execution, but still parallelizes, schedules, and optimizes the execution. I have not found good documentation or resources on migrating TensorFlow 1 code to TensorFlow 2. The official TensorFlow migration guide provides a high-level overview and then covers some special use cases at a very low level. The most useful resource I found was what appears to be an archived copy of an official guide published back when TensorFlow 2.0 was first introduced. So I searched for a simple TensorFlow 1 example that I could migrate for my audience. I found this GitHub gist by Ji-Sung Kim, who apparently used to work at Google. Let's take a look at what it does. I'll skip past his very comprehensive comments because you can study them at your leisure. This script runs a simple feed-forward neural network, also known as a multilayer perceptron. It starts by specifying dimensions for the input and output vectors. Here, it creates placeholders for the examples x and the labels y. Placeholders are kind of like variables in the TensorFlow graph that can be fed values from ordinary Python code. The intermediate layer of the network takes the examples placeholder as input and produces an output with 12 dimensions. The final layer of the network takes the intermediate layer's output and produces an output with the previously specified number of dimensions. 1. The loss function takes the labels placeholder and then subtracts the output of the final layer and then squares the difference. At this point, TensorFlow has created a graph that looks something like this. I've used a different shape for the intermediate and final layers to indicate that they contain many weights and biases. Next, the script creates an optimizer object. Without any parameters, the optimizer assumes a default learning rate. During training, the optimizer's job will be to calculate the gradient of the loss with respect to the weights and biases and adjust them to minimize the loss. The graph now looks like this. Next, the script creates an initializer object. The initializer object's job will be to set the initial values of the weights and biases. Next, the script creates a session object. A session object is required to execute any part of any graph. Now begins the training for 2000 epochs. X data and Y data are NumPy arrays, which behave like ordinary Python objects. X data is a batch of 500 examples of random input data. Y data is a batch of 500 random labels for the examples. feed_dict is a dictionary associating the placeholder variables to the Python objects. This is how TensorFlow 1 knows which placeholders get fed which data. Now that actual values are associated with the placeholders, it becomes possible to execute the computation graph. This session.run statement says to perform the trainOp operation using the specified feed_dict. Remember that trainOp was set to the optimizer instantiated with the loss graph. This means that when trainOp is executed, both the forward and backward passes are performed. The batch of examples and labels is fed to the placeholders. The intermediate layer uses its weights and biases to generate 12 outputs from the placeholders. The final layer uses its weights and biases to generate one output from the outputs of the intermediate layer. The output of the final layer is subtracted from the labels. The result is squared. The optimizer calculates the gradients of the result with respect to the weights and biases in the intermediate and final layers and adjusts them to minimize the loss. After this is done 2,000 times, the script generates a test batch of 5 examples of random input data. The new feed dict associates the examples placeholder variable with the test examples. Estimated targets was set to the final layer. This means that when estimated target is executed, only the forward pass is performed. The test batch is fed to the examples placeholder. The intermediate layer uses its previously trained weights and biases to generate 12 outputs from the placeholders. The final layer uses its previously trained weights and biases to generate 1 output from the outputs of the intermediate layer. Finally, the script prints out the test examples and the output of the network. Alright, I've downloaded this script as original.py. It obviously won't work because I have TensorFlow 2 installed. TensorFlow 2 does come with a script that starts the migration process from TensorFlow 1. It does string replacements of common TensorFlow 1 calls with their equivalent TensorFlow 2 calls in the compat.v1 namespace. Let's run that now. Alright, that seems to have worked. This didn't work when I tried it on the Efficient Neural Architecture Search repository. So I did replacements like these by hand as and when I encountered errors. All of these uses of the compat.v1 namespace do make the code look very brittle. Let's see if it runs yet. Now we get a different error. We can get past this by disabling eager execution at the top of the script. All right. Sure enough, the script is running, but it's generating deprecation warnings. Let's make a copy and then try to get it running with proper TensorFlow 2 calls. First, let's get rid of these imports from future. We'll allow eager mode execution for ease of debugging. In eager mode execution, TensorFlow 2 doesn't need placeholder variables, so we can delete these lines. Now, the TensorFlow 2 version of the dense layer is instantiated like this. For the input shape, we'll use the same shape as was used in the placeholders. In TensorFlow 1, these instantiations return parts of a graph. But in TensorFlow 2, they return functions callable from Python. In TensorFlow 1, we passed intermediate layer into the constructor for final layer. This told final layer to get its input from the output of intermediate layer. In TensorFlow 2, we'll simply compose these callable functions. In TensorFlow 1, the loss computation was represented with a graph. In TensorFlow 2, we'll define it as a callable function. The atom optimizer is instantiated in TensorFlow 2 as follows. It's a regular Python object. In TensorFlow 1, the minimize method returned part of a graph that we assigned to trainOp. In TensorFlow 2, we'll define trainOp as a callable function. In TensorFlow 1, the minimize method was given the loss portion of the graph. It would automatically adjust the weights and biases of both layers in the graph. In TensorFlow 2, minimize is receiving the loss value. We have to provide a list of the relevant weights and biases explicitly so it knows what to adjust. There is one more thing. When the loss function is executed, it has to be told to calculate and save gradients for use by the optimizer. We do this by executing the loss function and the minimize method in the context of a gradient tape and passing the tape to the optimizer. In TensorFlow 2, we don't need an initializer or a session, so we can delete these lines. We also don't need a feedDict object because we can pass NumPy arrays directly to the functions we just defined. We can call the trainOp function directly instead of in the context of the session. We can remove the feedDict for the test data. We can call final layer directly instead of in the context of a session. We just have to remember to call it on the output of intermediate layer. Let's try running the code. The code is running, but it's taking a lot longer than the previous version. Remember that TensorFlow 1 knew from the graph all of the computations that were planned. It could parallelize, schedule, and optimize them for fast execution. In this code, there is no longer any sign of any graph, only ordinary Python calls to various TensorFlow functions. However, we can decorate the functions we defined with tf.function. The tf.function decorator allows an ordinary Python function making TensorFlow calls to be executed as a graph that has been parallelized, scheduled, and optimized for fast execution. Now we get an error referring to line 73. It looks like the results of estimated targets are float32, while the labels are int64. Python did an implicit cast of the values for subtraction, but the graph execution environment did not. Let's convert the labels to float32 explicitly using the TensorFlow 2 cast method. The code is now executing at high speed and without any deprecation warnings. In this episode, we reviewed a simple example of a TensorFlow 1 training script. It represented a multilayer perceptron, loss function, and optimizer as a computation graph. Using the TensorFlow conversion tool and after disabling eager execution, we got the original script working in TensorFlow 2. But it used calls from the compat.v1 namespace and gave deprecation warnings. We converted the script to use mainstream TensorFlow 2 calls. We were able to remove placeholders and a global variable initializer. We were able to replace variables that were referring to the graph with ordinary Python functions. The script ran without deprecation warnings, but took longer to execute. We decorated our functions with tf.function to enable graph execution with parallelization, scheduling, and optimization. After adding an explicit cast, the script ran successfully at the expected speed. Thanks so much for tuning into this episode. If you found it instructive or useful, please share it with others who might as well. Don't forget to click the like and subscribe buttons, and I also welcome all of your constructive comments.